Hello. So let's continue with determinants, capsule 7B. And now we come to computational issues of determinants. Of course, you are not going to be able to write down all the n factorial terms, and the expansion of the determinant is going to make a big mess. We need a more efficient way to compute the value of a determinant, and there are many efficient ways of doing it. You already computed determinants in class 12, 3 by 3 determinants, but more or less those ideas will generalize to n by n determinants. Column operations can be used because by the very properties of determinants, that adding to a column, a multiple of another column doesn't change the value of the determinant, etc. Later, we shall see that row operations can also be used. So in fact, both of them can be used in tandem. But please use column operations only for computing determinants. Do not use it for solving systems of linear equations such as ax equal to b or to find a inverse, because in this particular course, we'd like to keep things simple and not cause confusion. So don't use column operations for solving ax equal to b or for finding a inverse. So recall that determinant of C1, if I replace the second column by a C2 prime plus b C2 double prime, then I get that value of the determinant is a linear combination of these two values. A times determinant C1 C2 prime dot 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 Cn, b times determinant C1 C2 double prime dot 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 Cn. So now I'm going to take a equal to 1, b arbitrary, and I'm going to take C2 prime to be C2 and C2 double prime to be C1. Then this equation reads determinant of C1, C2 plus BC1, comma, C3 dot 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 Cn equal to determinant of C1, C2, Cn, because A was 1, plus B times determinant of C1, C1, da da da, because C2 double prime was C1. But the two columns are equal here, so the determinant is 0. And so you get determinant of C1, C2, Cn. So what does this rule say? So we see that adding, nothing sacred about first column and second column. You can play this game with any pair of columns. In short, you get the rule that adding to a given column a multiple of another column does not affect the value of the determinant. All right. Again, you could take a to be 0. For example, I could take a to be 0 and C2 double prime to be C2 itself. Then what will happen to this? Then this will simplify to determinant of C1, B, C2, C3 dot 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 Cn is B times determinant of C1, C2, Cn. In other words, multiplying a given column by a real number B has the same effect as multiplying the value of the determinant by B. The third condition is skew symmetry. Interchange of two columns changes the sign of the value of the determinant. Now to proceed further, we will need the second fundamental lemma in linear algebra. There was already a first fundamental lemma. Calling it the first fundamental lemma means that there must be a second one lurking in the background, and here it is. F is a function from Rn cross dot 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 cross Rn to R. It's a multilinear function. Then the following are equivalent. F is skew symmetric. F of C1, if two of the slots are equal, then if I put the same thing in the ith slot and the jth slot, then the value of the function is 0. The third condition is that if I put the same input into adjacent slots, say Ci and Ci plus 1 take the same, are identical, then the value of the function is 0. These three conditions are equivalent. 1 implies 2 is quite obvious. Why? Because if I Ci and Cj were to be equal, if I put the same thing in the ith slot and the jth slot, then swapping the ith and the jth columns on the one hand will not change anything because they're equal. On the other hand, it will pick up a minus sign by the fundamental rule of skew symmetry. So you will get f equal to minus f, or f is 0. So 1 implies 2 is quite easy to see. 2 implies 3 is completely trivial, because in 2 we are demanding that the function should take the value 0 when any two slots are identical, In 3, we are making a less stringent demand. Namely, we are saying that the function should be 0 when adjacent slots are identical. So 3 is a much weaker condition than 2. At least prima facie it's weaker. So 2 implies 3. But then in hindsight, it's not really weak. It is equally strong. That's what we're going to prove. 3 implies 1. We're going to prove 3 implies 1. 3 implies 1 is quite easy. 3 implies 1 is a simple exercise. Now you're going to be a little worried. I call it a second fundamental lemma because it's going to be used very critically. And so such a critical thing, how can I leave it as an exercise? Okay, let us see. I'll just get you started and I'm pretty sure that you will be able to complete it easily. First of all, we are going to assume 3, right? So let us for illustration purpose, assume that let us do it for the first and the second column. I put the same entry in the first and the second column. I'm going to get 0. So which entries I'm going to put? I'm going to put C1 plus C2. So f of C1 plus C2, comma C1 plus C2, comma C3 Cn is 0. After that, I'm going to take another one. F of C1 comma C1 comma C3 Cn is 0. And yet another. F of C2 comma C2 comma C3 Cn equal to 0. Now what am I going to do? I'm going to use multilinearity. This is important. F is a multilinear function. So multilinearity has to be used. How are you going to use multilinearity? You're going to expand this. The first slot is the sum of two things. So I'm going to say f of C1 comma C1 plus C2 comma Cn plus f of C2 comma C1 plus C2 comma C3 Cn is 0. Now you're going to use multilinearity, but with a second slot, no? And you're going to get how many terms? So from this, you got two terms, and each of the two terms, there's a C1 plus C2 in the second argument. So that again going to give me two terms. So I'm going to get all in all 4 terms. In these 4 terms, one of the terms is going to be f of C1 comma C1 comma C3 Cn. That drops out. And another term is going to be f of C2 comma C2 comma C3 comma Cn. That also drops out. So which 2 terms survive? F of C1 C2 Cn plus f of C2 C1 Cn, and the sum is 0. So this means that if I swap the first and the second columns, I pick up a negative sign. Now you'll agree with me that this game can be played with the second and the third column, the third and the fourth column, the fourth and the fifth column, etc. So you will agree with me that this hypothesis 3, condition 3 enables us to prove that swapping to adjacent columns causes a sign reversal in the value of the function. Now, from adjacent columns, I want to now move on to the more general thing. What happens when I swap 2 non-adjacent columns? Then what happens? I make a transposition of Ci and Cj, where I and j may be far away. J will not be equal to I plus 1, or I is not equal to j minus 1. So what do? Now remember that swapping what is the swapping of I and j? It's a permutation. It's a permutation which is a simple transposition of 2 symbols I and j. But this permutation, this swapping can be brought about by a sequence of adjacent swaps. Is that correct? Suppose, for example, you got 5 things, 1, 2, 3, 4, 5, and I swap 2 and 5. I swap 2 and 5. So what has happened? 1, 2, 3, 4, 5. I have swapped 2 and 5. So 1, 5, 3, 4, 2. So the swapping of 2 and 5. The question is that do you agree with me that the swapping of 2 and 5 can be brought about by sequence of adjacent swaps? So first I swap 2 and 3. So I get 1, 3, 2, 4, 5. After that I swap 2 and 4. After that I swap 2 and 4. I get 1, 3, 4, 2, 5. After that I have swapped 2 and 5. I get 1, 3, 4, 5, 2. So 2 has gone to the last position as I wanted. Now I want 5 to come to the second position. So I'll swap 4 and 5, etc. So do you agree with me that this swapping of 2 and 5 can be brought about by can be carried out through a sequence of adjacent swaps? Now the question arises, how many such adjacent swaps do I need? I will need an odd number of adjacent swaps. And each adjacent swap is going to be pick up a minus sign, because I just proved that hypothesis 3 now implies that swapping two adjacent columns will pick up a minus sign. But now I'm going to do an odd number of swaps of adjacent columns, and I'm going to bring, and that is going to have the effect of swapping two specific non-adjacent columns, Ci and Cj. Now the question that I want to ask you is that how do I know that I need an odd number of successive exchanges, successive adjacent swaps? How can I be sure that it's odd? I want you to think about the number of inversions. Is a swapping, is it an odd permutation or an even permutation? Think about that. It's an odd permutation. So I'm carrying out that odd permutation. I'm bringing about that odd permutation by some lengthier process. Remember, the parity will not change. So the parity of the permutation is already odd. So even if I bring about that swapping of two non-adjacent columns through a sequence of adjacent swap, the number of swaps needed will again be odd. So how many times do I pick up a minus sign? An odd number of minus signs. So I left to the minus sign. So swapping any two columns, adjacent or otherwise, picks up a minus sign. That completes the proof of the second fundamental lemma. I have not written out all the details because I would like you to listen to what I said. I'd like you to take specific permutations like 1, 2, 3, 4, 5 and swap things and check it out for yourself and write out the details. It's far more instructive to do so. Now let's come to computations. Let us start with the 2 by 2 matrix. And let's find the determinant of a 2 by 2 matrix. Determinant of A11, A12, A21, A22. What is that? That is determinant of the first column is A11, E1 cap plus A21, E2 cap. Second column is A12, E1 cap plus A22, E2 cap. Use multilinearity. When you have E1 cap, E1 cap, it's going to be 0. When you have E2 cap, E2 cap, it's going to be 0. So the terms are E1 cap, E2 cap and E2 cap, E1 cap. When you see E2 cap, E1 cap, make a swap and bring it E1 cap, E2 cap. So you're going to get A11, A22 minus A12, A21. And you're going to get determinant of E1 cap, E2 cap. And that is 1. So you get the familiar formula for the determinant of a 2 by 2 matrix. For a 3 by 3 matrix, we have seen that this determinant is a sum of 6 terms. 3 of them appear with plus signs and 3 of them appears with minus sign. I want you to write down all the 6 terms. I want you to write down all the 6 terms in detail and check that that expression exactly equals A11 times the 2 by 2 determinant A22, A23, A32, A33. Now, how did I get this smaller square A22, A23, A32, A33? Delete the row and the column containing A11. Delete the row and the column containing A11. You get a smaller matrix, 2 by 2 matrix, and that is A22, A23, A32, A33. Minus A12. Note down the minus sign. Minus A12. Delete the row and the column containing A12. You get A21, A23, A31, A33. Plus A13. Delete the row and column containing A13. You'll get A21, A22, A31, A32. You're going to get exactly this, and these 2 by 2 determinants we already calculated, no? You have to use this, the formula for the 2 by 2 determinant, and you're going to get this. This is called expansion using the first row. This is called expansion using the first row. Check that the same expression can also, check that the same thing can also be obtained by A11 times, delete the row and column containing A11, A22, A23, A32, A33. This time I'm going to take A21, delete the row and column containing A21. You get A12, A13, A32, A33 with a minus sign, of course. And the third thing is I'm going to use the third one, A31. Delete the row and column, you get A12, A13, A22, A23. So you get that. So this is called expansion. This is called the expansion using the first column. Now I want you to check that no matter whether you use the first row or the first column, you're going to get the same thing. You're going to get the same combination of 6 terms and the same distribution of plus ones and minus ones. The last expression is called expansion with respect to the first column. Now again, I could expand with respect to third column, for example. And then the third, how do I expand it with respect to the third column? A13, delete the row and column containing A13, A21, A22, A31, A32. Then minus A23, delete the row and column containing A23, A11, A12, A31, A32, etc. So expansion using the third column. That will also give you the same set of 6 terms. What about expansion using the second column? Be careful with the signs or expansion with respect to the second row. Do that. So do these expansions and say that observe that there are 6 ways in which you can expand the determinant using any of the 3 rows or any of the 3 columns, and you get the same long expression that we wrote, with 3 with plus signs and 3 with minus signs. Now the question that I want you to ask is, can you formulate a general rule? Can you formulate a general rule for 4x4 matrices, 5x5 matrices, n cross n matrices? Of course, you're going to guess this rule naturally by looking at this pattern. And after you guess this rule, I'm sure you'll guess it correctly, but you have the job of proving it algebraically, right? How would you prove it algebraically? Are you going to write down all the n factorial terms and do get into a big mess? No. The proof in the general case is going to follow a very different line of reasoning. We are not going to write down all the n factorial terms and get into a big mess. We are not going to do that. We are going to do it a little more intelligently, and we're not going to. So the 3x3 determinant, you could do it because there are only 6 terms. For the n cross n determinant, you can't do it. We have to do it more cleverly. The uniqueness theorem that we proved is going to come to our rescue in avoiding all the prosaic drudgery. Before formulating and proving the general theorem, we need a couple of terms. First is that, observe that we deleted the row and when we did A11 times a 2x2 determinant. What is the 2x2 determinant? We deleted the row and column containing A11. That small 2x2 determinant is called the minor of A1. And then we got A12. We deleted the row and column containing A12. We got another small determinant that's called the minor. But there is a small thing in the side. We had to put a minus sign there. And so let us give these things a name: minors and cofactors. So again, we are going to start with an n cross n matrix Aij. So delete the row and column containing Aij. You get a n-1 times n-1 submatrix. And that submatrix, you take the determinant of that submatrix, and whatever you get, call it Mij. This Mij is going to be called the minor of Aij. It's called the minor of Aij. And the minor with a sign attached is called the cofactor. What sign are you going to attach to a minor? I'm going to attach the sign -1 to the power I plus j, and I'm going to call this new thing the cofactor. So cofactor equal means minor with appropriate sign. What is that sign? It is -1 to the power I plus j. So the expansion of this is so capital Aij is the cofactor of little aij. So if with this notations, the expansion for a 3x3 matrix using the first column can now be neatly written as A11 into capital A11 plus A21 times capital A21 plus A31 times capital A31. Very neat appearance of the expansion using the first column. Expansion of the using the first row also has a very neat appearance: A11 capital A11, A12 capital A12 plus A13 capital A13. And we are checked that all these things give the same result. Both expansion of the first row and expansion of the first column, they give you the same result. So what will be the expansion? What will be the formulation for the n by n case? The formulation for the n by n case will be expansion using the ith row, summation aij, capital Aij, j from 1 to n. This is called expansion using the ith row. What is the expansion using the ith column? Summation I from 1 to n, aij, a capital Aij. So when I'm expanding with respect to the ith row, I is fixed and j is varying. When I'm expanding using the jth column, j is fixed and so I is varying. So the summations are appropriately going from j from 1 to n and I from 1 to n. It's a remarkable fact that these two numbers are going to be the same, and they're going to be the same no matter what I you take here and what j. You can expand with respect to any row, you can expand with respect to any column, you're going to get the same number, and that is the determinant of A with that n factorial terms with pluses and minuses distributed. And that is the expression that's going to come out finally, and that is the value of this. So the fact that these are both these ways of expanding, where I is arbitrary or j is arbitrary, is going to cough out the same. This is going to cough out the same number, summation epsilon I1 I2 in a I11 a I22 dot 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 a in n. So first we shall prove that the row expansions, the expansion with respect to any row will give the value of the determinant like this. I mean, we are going to later on, it will follow trivially that expansion with respect to any column will also give you the same result, because this will follow at once when I prove that determinant of A equal to determinant of A transpose. Moment I say the determinant of A equal to determinant of A transpose, then it will immediately follow that whether you expand with respect to the any row or whether you expand with respect to any column, you're going to get the same thing. So how to prove the determinant of A equal to determinant of A transpose? That will be the very last slide. That will be the very last slide. Okay. So for a n cross n matrix A, determinant of A equal to summation j from 1 to n aij, capital Aij, expansion using the ith row. Let us prove the theorem. The theorem is proved by induction on n. The case n equal to 2 is completely trivial, and so we are going to assume that n is greater than or equal to 3. We are going to assume that the theorem has been proved for n minus 1 by n minus 1 determinants. Okay, so let us take some I is fixed, and let us look at summation j from 1 to n aij, capital Aij. Let us call this number f of C1, C2, Cn, where C1, C2, Cn are the columns of the matrix A. First of all, check that f of E1 cap, E2 cap, if I do this expansion with the identity matrix, I'm going to get the number 1. That is left for you to check. Now it is very easy to see that this function is multilinear. This expression that I written down, summation j from 1 to n aij, capital Aij, is multilinear. In each is multilinear. So let us take, for example, let us check multilinearity of the kth column. Suppose a ck is split as alpha ck prime and beta ck double prime. Then look at the summed. That there one of this for one particular j, so j equal to, let us look at the j equal to k term. What I'm going to get? Summed aik, capital Aik. Remember, when I form the cofactor, of Aik, the kth column is not going to be there. So the kth column is not going to be there. When I take alpha ck prime plus beta ck double prime in the kth place, it's not going to affect the cofactor. So the cofactor is going to be again aik only. Okay, but little aik, but this aik, that will basically be aik prime and with the alpha thrown in, and aik double prime with the beta thrown in. So this term aik, capital Aik, will just be the sum of these two terms. And now look at what happens when j is not equal to k. When j is not equal to k, when j is not equal, so when j is not equal to k, the aij doesn't change, no, because you're tampered the kth column only, and j is not equal to k. So aij is going to remain intact. What is going to happen is that the one of the columns of aij is going to be broken into a linear combination of two columns. So likewise, the cofactor is going to become alpha times aij prime plus beta times aij double prime. So all in all, you will realize that this expression is multi. So in all the terms, there will exactly be this alpha times the corresponding expansion plus beta times the corresponding expansion with the double prime. There will be two terms: alpha times the corresponding expansion with a single prime, and beta times the corresponding expansion with a double prime thrown in. So that will immediately convince you that multilinearity holds. You have to do this. If you're not convinced, do it for a 3x3 case or a 4x4 case and check it for yourself. So multilinearity is fairly obvious. What is not obvious is skew symmetry. Skew symmetry is going to be a little tricky business, and this is where the second fundamental lemma is needed. Okay. Now, what I'm going to do is that I'm going to show what we're to show is that this expression that you see here vanishes summation j from 1 to n aij capital Aij. When I think of this as a function of the columns of the matrix, I'm going to get 0 when ck and ck plus 1 are equal. Then I take two adjacent columns to be equal, then I'm going to get the value 0. But once I prove that by the second fundamental lemma, it will follow that this function is skew symmetric, and if it is skew symmetric, then it has to be the determinant of A by uniqueness. So how to prove that that when the columns k and k plus first columns are identical, then I'm going to get 0. Okay, so now suppose now let us look at this now let us look at this term. If j is not equal to k or k plus 1, if j is not equal to k or k plus 1, then two columns in the cofactor are going to be identical. If j is different from k or k plus 1, then the two columns in this cofactor are identical, and that cofactor will disappear by induction hypothesis. And on the other hand, so this entire summation j from 1 to n aij capital Aij, all we are left is with it should be aik capital aik plus 1 capital aik plus 1. I think it should be k and k here, and k plus 1 and k plus 1. I will make a change before sending you the slides. But remember, aij is the same as aik is the same as aik plus 1, because the kth column and the k plus first column are identical. Remember, so I can pull out this aij, aik, and aik plus 1 out and write it simply as aik. What am I going to get? Capital aik, capital aik plus 1. Now, how do I know this capital aik plus capital aik plus 1 are they combine to give you 0? But what is capital aik? Compare it with the minor mik. Compare this with the minor mik plus 1. The minors are identical because the columns, because here I'll be omitting the kth column, but the k plus first column is there. Here I'll be omitting the k plus first column, but the kth column will be there, and those two matrices will be identical. The minors will be identical, but the cofactors will be the minors with appropriate signs, right? Minus 1 to the power I plus k, minus 1 to the power I plus k plus 1, and that will be 0. And so we have checked, that this expression satisfies the property that when adjacent columns are equal, the value is 0. So with the second fundamental lemma, f is skew symmetric, and so by the uniqueness, this must be the determinant. And we have completely proved, we have completely established the theorem that the determinant, you'll get the value of the determinant when you expand it using the first, when you're using any row. We shall soon prove that determinant of A equal to determinant of A transpose, from which it should be evident that expansions by rows or expansions by columns give the same result. Now, I'm giving you a reference for these things. There is a book by Serge Lang, Linear Algebra, the second edition. I like the second edition most. Lang wrote several books on linear algebra, various with variants. And this is a book which I like the best. It was published by Edison Wesley in 1972. The second edition appeared in 1972. From pages 167 to 202, you will find this discussion. And there will be lots of examples in Lang's book. You can also read that with profit. So we will take one simple example: 2022, 2021, 2021, etc. Well, obviously, I'm going to make column as I'm going to subtract from column 3. I'm going to subtract column 2, and from column 2, I'm going to subtract column 1. I'm going to get this. I'm going to get this easier determinant, and I'm going to add to the first column 2022 times the second column, so that this becomes 0, and I'm getting 4043. Now expand using the first row. Expand using the first row minus 1 times the smaller 2 by 2 determinant, and that completes the job. So this is, please carry out this calculation. The second example is that of a circulant ABC, BCA, CAB. This is called a circulant matrix. So I should add to the third column the first column and the second column. I'll get ABC, BCA, A plus B plus C. And so A plus B plus C comes out, and I'm getting AB1, BC1, CA1. Now I'm going to make further column operations. Subtract from the first column A times the third column. Subtract from the second column B times the third column. I'm going to get 0, 0, 1. B minus A, C minus B1, C minus A minus B1. And now expand using the third row, expand using the first row, excuse me. I'm going to get A plus B plus C, B minus A, C minus B, C minus A minus B. So it's going to be A plus B plus C into minus C minus A, C minus B, minus A minus B the whole squared. And I get this expansion. This is a... So, okay, so I will stop this second capsule here, and we will take up some